Hello students, welcome to this module on linear algebra, which is part 12 of our series of modules on linear algebra. In this module we are going to discuss the solution of simultaneous linear equations, and we will derive the conditions under which a system of linear equations have solutions and so on. First of all, it's useful to understand what is a linear equation. For example, if you have 5x plus 2y is equal to 6, this is an example of an equation in the variables x and y, and both x and y occur linearly, right? Because you see the occurrence of x only once here, and the occurrence of y occurs only once here, and these are some coefficients which are numbers 5 and 6, 5, 2 and 6. So this is an example of what we call a linear equation. This is a single linear equation. Of course, we are not interested in just a single linear equation. We are interested in a system of linear equations. For example, 3x plus 4y plus 2z is equal to 7, 7x minus 6y minus z is equal to 3, minus 3x. I'm just writing something offhand. So this is a example of a system of three linear equations. Because why is it linear again? Because all the variables x, y, z occur only once. Okay, three linear equations in three unknowns. Okay, now an example of a nonlinear equation is, of course, you might have 3x to the 4 minus 4x cubed minus 6x squared plus 7 is equal to 0. This is an example of a nonlinear equation. Why is it nonlinear? Because the variable x occurs in powers higher than 1. Okay, and you can also have nonlinear equations in more than one variables. You could have 3x to the 8 minus 7 y to the 4 or something. Okay, this is an example of nonlinear equation again, but in two variables x and y. There are also other equations which are nonlinear, but they are not polynomial, but they are called transcendental. For example, you might have e to the x minus 3 x plus 4 is 0. Here you have e to the x, which is a nonlinear function, but it's not a polynomial function. These are called transcendental functions. So for example, you might have sin hx, cos hx, and so on, ln x. These are all, when you have an equation where the unknown appears within such functions, these are called transcendental equations. And these are nonlinear, but these are not just polynomial nonlinear equations. These are called transcendental equations. Okay. Now the focus, of course, of this lecture is not on nonlinear equations. I just wanted you to understand what is meant by, what is the fundamental distinction between linear and nonlinear equations. We are going to look at a system of simultaneous linear equations of the form a11 x1 a12 x2 plus a1n xn is b1, a21 x1 plus a22 x2 plus a2n xn is b2, all the way going up to am1 x1 plus am2 x2 plus amn xn is bm. Okay, so you have a system of m equations containing n unknowns. Okay, this is the first equation, this is the second equation. Likewise, you go on all the way up to m equations, and the number of unknowns are x1, x2, so on up to xn. In general, m need not be equal to n. You could have m greater than n, m equal to n, m less than n as well. Okay. All right. So now, if you want to write this in a more compact form, you could appeal to the use of matrices. You could write a11, a12, a13, a1n, so on up to am1, am2, amn, just to indicate that the vector m is not equal to n. I am writing the vector slightly longer, x1 so on up to xn. This is equal to b1 bm. Okay, this is an m by n matrix, whereas this is an n by 1 column vector, giving rise to an m by 1 column vector. These are the coefficients. So you can write in a more compact manner. The same information can be represented as the matrix m by n matrix A multiplying the vector x, giving rise to b, where x is an n by 1 column vector, whereas b is an m by 1 column vector. Now typically b is known and the components of the matrix A are known. Okay, and x is the unknown. So when you say solution, you want to know, if you are given b and a, what is that x that provides a solution to this equation, that is a solution that satisfies this equation. Okay. Now one more jargon. If you have a x is equal to b, okay, such an equation is called an inhomogeneous equation. If the vector b is not equal to 0, it's called an inhomogeneous equation. If b is 0, then you have ax giving rise to 0. Such an equation is called a homogeneous equation. Okay, right. So we are interested in understanding under what conditions will this have a solution, either inhomogeneous or homogeneous, provided A is an m by n matrix and x is an n by 1 vector. Okay, we will also consider the special case of m equal to n, where you have the same number of equations as unknowns. In general, the number of equations m is not the same as the number of unknowns n. Okay, so what are the scenarios for the solution of ax equal to b? You can have three scenarios. You can have a unique solution. You can have no solution. And you can have infinitely many solutions. Okay, so these are the three possibilities. How do you understand these possibilities? Consider the simplest case, where m equals to 1, n equals to 1. That is, you have only one equation and one unknown. So you have a single equation. You just have something like this: a11 x1 is b1. Let's consider the three cases. If a11 is not equal to 0, then you can write x1 as simply b1 by a11. This is an example of a unique solution. Okay. Now you could also have a11 is 0 and b1 is not equal to 0. Then you're saying that 0 times some number is a non-zero number. This means that there is no solution that satisfies. This is called an inconsistent equation. Okay. Now finally, we also have, if both a11 is 0 and b1 is 0, then any x1 will satisfy this equation. So this means you have infinitely many solutions. So it's clear that even in the case of a single linear equation, you can see the three scenarios: unique solution, inconsistent equation or no solutions, and infinitely many solutions. Now, how are we going to generalize these notions to n by n systems, and how do you find the criteria under which you have these three categories: unique solution, no solution, and infinitely many solutions? That is the objective of this module. Okay. Now, first of all, let's look at the system of linear equation. Ax is b. Okay. Now, you can think of A as a collection of column vectors c1, c2, so on up to cn, because A has m rows and n columns. So if I call each of this is a11, a21, am1, a12, a22, am2, a1n, a2n, amn. If I call each of this if I call this as C1, sorry, if I call this as C1, and then if I call this as C2, and so on, then I can write this equation, linear equation, system of linear equations, as the collection of column vectors which form A Cn multiplied by this column vector x, which is x1, x2, so on up to xn, is equal to b vector. If I use elementary principles of multiplication of vectors, so I can write this as x1 c1 plus x2 c2 plus so on up to xn cn is b. Okay, or in other words, I can write b as x1 c1 plus x2 c2 plus all the way up to plus xn cn. Now this is a known vector. B is known, and c1, c2, so on up to cn are known, whereas these are the unknowns. x1, x2, xn are the unknowns. Okay, so what does this represent to you? This implies that the system of linear equations Ax equal to b can be thought of as, so the solution of the system of equations Ax equal to b, where x is the column vector of unknowns, can be thought of as the equivalent to a problem wherein you are trying to expand a known vector b in terms of the vectors c1, c2, so on up to cn, and the coefficients of that expansion are x1, x2, so on up to xn. So when can we, then the question, so we are basically boiling down this problem, or the solution of this problem is equivalent to solving the solution of these unknown coefficients of this expansion of the known vector b in terms of the column vectors of A, c1, c2, so on up to cn, and the coefficient of that expansion can be thought of as the unknown solution vector x. Okay, now let's so there are many cases that we can think about based on our earlier knowledge of or discussion of linear algebra. Okay, let's take the simplest few cases and let's try to develop our intuition in this problem. So these are some simple examples. Let's take m is equal to 2, n is equal to 3. You have two equations, three unknowns. So the problem will look like x1 times a11 a21 plus x2 times a12 a22 plus x3 times a13 a23 is equal to b1 b2. Remember that this is known, these are all knowns. Okay, so the only thing that we are interested in finding are x1 x2 and x3. Okay, so here you have these vectors, these column vectors. Let's call this c1 c2 c3. Now these are vectors in 2D, right? Because there are only two components to these vectors. These are 2D vectors. In 2D you will almost have, or at most two linearly independent vectors, right? You can have only two linearly independent vectors in two dimensions. That is a definition of the dimension of a space, right? That's what we have discussed long before in our modules. Therefore you can have only two linearly independent vectors. Okay, you have but you are trying to expand a vector in 2D space in terms of three vectors. Okay, but this cannot be a unique expansion, because in a 2D space you can at most have two linearly independent vectors, let's say c1 and c2. You cannot have one more vector c3. C3 cannot be linearly independent. It will be linearly dependent on either c1 or c2. Okay, so that means that this expansion cannot be unique. That means that the solution set x1 x2 x3 cannot be unique. Okay, so when you have ax equal to b with m less than n, you have less equations than unknowns, then the solution, if it exists, cannot be a unique solution. Of course, the question is whether the solution exists at all. That's something that we'll come to, but I'm trying to generally motivate that if m is less than n, you cannot expect unique solutions. Okay, so this is something that you can keep in, you can understand based on what we have discussed in terms of vector spaces so far. Now let's consider another example where, let's say, you have m is equal to n is equal to 3. So you are trying to expand b in terms of the column vectors of a. Okay, so here we have a vector in 3D. So because m is equal to n is equal to 3, so b is b1 b2 b3. So c1 is a11 a21 a31 and so on. You have three such vectors. So we are trying to expand this vector in 3D in terms of three vectors c1 c2 c3. So this is possible as long as c1 c2 c3 are linearly independent and the collection b c1 c2 c3 should be linearly dependent. Only then, if only this four set of vectors are linearly dependent, you can express b in terms of c1 c2 c3. Okay, so in order for this system to have a solution, this means that the column vectors forming A must be linearly independent. Okay, only then you have three linearly independent vectors in a 3D space, and the vector B in combination with c1 c2 c3 must be linearly dependent. Only then you can express B in terms of all the other three basis vectors. If that is the case, then you can have a unique solution. So if all this is satisfied, then you can have a unique solution. Okay, but if c1 c2 c3 are linearly dependent, then the solution to this, like the previous case, cannot be unique. If it exists, it cannot be a unique solution. Okay, so these are the issues that come up when you think about, in general, solution of a system of m by n m equations and n unknowns. Now let's consider another example. Here we are going to consider more equations, m is equal to 3, than unknowns. You have 3 equations and 2 unknowns. You have m greater than n, that is more equations than unknowns. Okay. So this can be written like this. Suppose a11 x1 plus a12 x2 is equal to b1. a21 x1 plus a22 x2 is equal to b2. a31 x1 plus a32 x2 is equal to b3. So you can write this as x1 times, again the same idea, sorry, c1 plus x2 times c2 is equal to b, where b, c1, c2 are are 3 by 1 column vectors, right? You have, these are 3 by 1 column vectors. Okay, so you are trying to expand a 3-dimensional vector b in terms of 3-dimensional vectors c1 and c2 alone. In principle, if you want to express any arbitrary vector b in terms of you need 3 linearly independent vectors, but you are left with only, you are given, as per this system, you are given only 2 linearly independent. We don't know whether they are linearly independent or not. At most you have 2 linearly independent vectors. That means that not any b can be expressed in terms of c1 and c2. Only those, suppose you look at c1 and c2 in 3D space. c1 can be, like this, and c2 can be like this. So c1 and c2, they will form a plane in 3D. Only if b lies on that plane will there be a solution. If I give you some other b which is not lying on that plane, that cannot be expressed in terms of these two basis vectors, because these two basis vectors c1 and c2 will form a plane in general, okay, whatever that is. That plane, that is a plane in 3D, and if I give you any b that is not lying on that plane, then you cannot find solution. That is inconsistent. Okay, so these are some of the simplest ways in which you can try and understand how and when solution exists for a system of linear equation. Okay, I try to give you a geometric picture depending on whether you have more equations than unknown or less equations than unknown, or identical number of equations and unknowns. Okay, so again, just as the case of a single equation that we started off with, in general a system of m equation and n unknowns also will have various possibilities. If there exists one or more solutions, then we call the system consistent. Further, under consistent systems, if you have only one solution, you call it a unique system, because the system has only one solution. But if the system has many solutions, the system is non-unique, because you don't have a unique solution, you could have many solutions. If there are no solutions, then the system is called inconsistent. Okay, now in all this, it's useful to introduce the notion of a rank of a matrix. There are two equivalent definitions for the rank of a matrix. The first definition is an m by n matrix has a rank R if it has at least one R by R submatrix. Out of that big matrix, you could identify one submatrix of dimension R, square matrix. This is a square matrix, which is a square matrix because the dimension is R by R with non-zero determinant. but no square matrix larger than R by R with non-zero determinant. Okay, this is the largest square matrix. R is the dimension of the largest square submatrix with non-zero determinant. Anything like R plus 1, you don't have a non-zero determinant. The determinant will be 0. This is one definition of rank. The other definition of which is equivalent to the previous definition, the rank of a matrix A is equal to the number of linearly independent column vectors in that matrix is also equal to the number of linearly independent row vectors in that matrix. So you can understand why the number of linearly independent column vectors is called the rank, because we just saw that Ax is equal to B can be written as B is x1 c1 plus x2 c2 plus xn cn, right? Whether B can be expressed uniquely in terms of these vectors c1 c2 cn, which are the column vectors of A, well, clearly depends on whether c1 c2 are linearly independent or dependent, right? If you have lesser than n linearly independent vectors, then the expression of B in terms of those vectors cannot be unique. You can always choose some other set of vectors and thereby making it non-unique, right? Because not all the vectors are linearly independent. Then the expression of this in terms of the basis vectors c1 c2 cn will not be unique if these are linearly dependent vectors. Okay, so based on this rank idea, right, you can generalize the existence of solutions to the system. You can stipulate the conditions under which this system has a solution based on the following rank criteria. You consider A is called the matrix of coefficient, the coefficients being A11, A21, A12 and so on, and B is the matrix of the right side. Now A is called the coefficient matrix, and if you consider this matrix A, and this is called the augmented matrix. This has the right side vector also present in it. So the rank, the solution of this system of linear equations depends on if the rank R of the solution matrix of the augmented matrix is not equal to the rank of the solution matrix, then there are no solutions to the system Ax equal to B. The reason is the following: if rank of A is, let's say, 3, and if rank of A and B put together, the augmented matrix is 4, that means that B is not linearly dependent. Okay, so it is linearly independent of the column vectors of A. So therefore you cannot express B in terms of A. That's the same idea you are trying to express in terms of rank. If you understand rank being the number of linearly independent vectors of A, then B should be linearly dependent on the column vectors of A. Only then you can express B in terms of x1 c1 plus so on up to x and cn, right? So this is the same idea stated in the form of rank, using the notion of rank. Okay, it has a unique solution if rank of A B is the same as rank of A, then it has a unique solution. Okay, now if rank of AB, if rank of AB is equal to rank of A is equal to n, the number of unknowns, then you have a unique solution. If rank of AB, the augmented matrix, is the same as rank of the coefficient matrix, but it is less than n, then you have the case of non-unique solutions. Okay, these are the conditions for finding when you have unique solutions, non-unique solutions, or no solutions. Okay. Now I'm going to illustrate this with the help of some examples. Now in order to do this, we appeal to what is called the Gauss elimination. The Gauss elimination is a procedure wherein you linearly combine rows and columns of the system of equations so as to get an upper triangular form of the resulting equations. So let's illustrate with the help of an example. Let's say you have three equations in three unknowns. And 3x1 plus x2 plus x3 is equal to 9. x1 minus x2 plus 4x3 is equal to 8. So let's number these equations 1, 2 and 3. You have m is equal to 3 equations and n is equal to 3 unknowns. Okay. Alright. Now let's transform these equations in the fall linearly combine. Equation 4 is the same as 1. Okay, sorry. Let's linearly combine. Let 1 remain the same and we'll call this equation 4. Let equation 2 change into be converted into minus 3 times equation 1, that is this, plus the original equation 2, and this we will call as, instead of equation 2, we will call this as equation 5. Now instead of equation 3, we will have minus 1 into equation 1 plus equation 3, and that we will call equation 6. So what are these three equations? 5 is basically minus 2x2 plus 4x3 is equal to 6. Equation 6 is basically minus 2x2 plus 5x3 is equal to 7, and of course the original equation remains as such as 4. x1 plus x2 minus x3 is equal to 1. Okay. Now we'll do a further, basically what we are saying is we want to reduce it such that the final equation should have only x3. Okay. So now 4 will remain the same, 5 will also remain the same, 6 will be converted as, so as to eliminate the first this term also, minus 2x2 minus 1 into 5 plus 6 to give rise to three equations. x1 plus x2 minus x3 is equal to 1, minus 2x2 plus 4x3 is equal to 2, x3 is equal to 1. So this can be represented like this, in matrix form like this, in matrix form like this: 1, 1, minus 1, operating on x1, x2, x3, giving rise to I'm sorry, this should be this should be 6, isn't it? I wrote it wrongly. Okay. 0, minus 2, 4, 0, 0, 1 is 1, 6, 1. Now this pattern is called an upper triangular matrix, right? Okay, this triangle, this pattern is called an upper triangular matrix because you have all the entries above the diagonals are in general non-zero. Okay, but all the entries below the diagonal are 0. This is called an upper triangular matrix. Why is it convenient? Why is it nice to have an upper triangular matrix? You can solve this system of equations sequentially. x3 is 1, then you substitute x3 here and find x2. Then you will find x2 is equal to minus 1. You know x1, x3 and x2. You substitute in equation 1 to find what is x1. You will get x1 is equal to 3. Okay, this is the solution. Now the upper triangular matrix also helps you to find the rank of a matrix. See, here you have 0, 0, 1, and so if you keep reducing, if the system is linearly dependent, you will end up with 0, 0, 0. Okay, then you will not be able to form a 3 by 3 determinant. But in this case, the determinant of this matrix is 3. So rank of A is 3. Okay. Now that is also the same as the rank of AB, the augmented matrix. Okay. Therefore, that means that if you consider the rank of the augmented matrix 1, 1, minus 1, 1, 0, minus 2, 4, 6, 0, 0, 1, 1. So what is the largest matrix, square matrix, which has non-zero determinant? Of course, it's 3 here, right? Because you cannot form a matrix higher than rank 3, order, right? So order 3. So it is 3. So this means that you have rank of A is equal to rank of the augmented matrix AB, which is the same as the number of unknowns. So you have a unique solution. So the Gauss elimination procedure helps you to figure out the solution rather easily, but it also helps you to figure out the rank quite easily. Okay. Now one thing that I would like you to remember with regard to this Gauss elimination, two linear equations, so two linear system of linear equations, two system of linear equations. So let's write it like this: two systems of linear equations with n unknowns are equivalent if their solution sets are identical. Note that in the previous case, you started off this equation, this system of equations. This is the original set of linear equations. After transforming, you got the upper triangular set. Because you have only linearly combined rows and columns, okay, the solution of this system will not change. Okay, so that is what we are saying here. Two systems of linear equations with n unknowns are equivalent if their sets are identical. Now, when can these be equivalent? If you do linear superposition of rows, that is, you can say that equation J plus alpha times equation K, if you call this new equation J, then that is an allowed operation. The solution set will remain the same, and you can say that equation J is alpha times equation J. You can multiply a given row or a given equation by a number, doesn't change anything, or you can interchange equation J and equation K or something. Okay, and that also will not change the solution. Okay. Now we saw a consistent system. Now let's take an example of an inconsistent system. System of equations. Okay, let's say you have 2x1 plus 3x2 minus 2x3 is equal to 4x1 minus 2x2 plus x3 is equal to 3. 7x1 minus x3 is equal to 2. You have three equations, right? Now I will do Gauss elimination in the usual way. The first equation will remain as such. The second equation will change into second minus half times 1. The third equation will change into the third equation minus 7 by 2 times 1. This will give rise to 2x1 plus 3x2 minus 2x3 is equal to 4 minus 7 by 2x2 plus 2x3 is equal to 1 minus 21 by 2x2 plus 6x3 is equal to minus 12. Okay, you have this after eliminating, you can verify that this is what will happen. Now we have only two variables in the third equation, so we have to only manipulate this equation to get into 1. So the third equation can be converted into minus 3 into the second equation, okay, out of plus 3. Okay, let's call this let's not call it 3 because we have already called this, so let's call this 4, 5, 6. So the sixth equation will change into minus 3 into 5 plus 6, and that will give rise to another equation which will appear like 0 is equal to minus 15. So after changing this equation so as to eliminate this, you will find that when I multiply minus 3 by 5, then I will get so what will I get? So I'll get minus plus 21 by 2x2, and then minus 6x3 is equal to minus 3, and then the sixth equation will be minus 21 by 2x2 plus 6x3 is equal to minus 12. So this cancels if I add up, but this gives rise to minus 15. So this is inconsistent. So that means that this system of equations cannot have a solution. Okay, so the Gauss elimination idea helps us to find out if there is a solution. It helps us to figure out the solution, but if you have an inconsistent system, then it will also tell you that there is no solution. Now instead consider the same system but with the last equation, 2x1 plus 3x2 minus 2x3 is equal to 4, x1 minus 2x2 plus x3 is equal to 3, 7x1 minus x3 is equal to previously we had 4, right? Sorry, previously we had 2 in the last expression. Now instead we have 17. Now you do Gauss elimination. You will end up with the following system of equations: 2x1 plus 3x2 minus 2x3 is equal to 4, minus 7 by minus 7 by 2x2 plus 2x3 is equal to 1. The final equation will become 0 equal to 0. So basically this system of three equations, after Gauss elimination you find that two of them are linearly dependent, therefore you effectively get only two equations for three unknowns. So you can take x3 to be some alpha, anything, it can be anything, any number, I'll call it as alpha. So then x2 becomes minus 2 by 7 plus 4 by 7 alpha, and then x3 becomes 17 by 7 plus 1 by 7 alpha. So this is called a one parameter. There are infinitely many solutions. It's called an one parameter family of solutions. That parameter being alpha. Alpha can be anything. Okay, alpha can be 0, 1, anything. Everything will be a solution for this system of equations, and x3 is alpha. Okay, so this is an example of infinitely many solutions, but this is specifically called a one parameter family of solution. Okay, so I'll stop here for this module, and we'll take it up, continue from here in the next module. Thank you.